Hello folks, so we're going to start our videos for Chemistry 112. 112 will go through general chemistry's a little bit more difficult topics, but largely it's going to build on some of the stuff we learned in 111. We had just finished off 111 with properties of gases. Now this chapter 112 will look at intermolecular forces and some of the properties of liquids and solids. Let's go ahead and get started. This first video will be looking largely at the intermolecular forces behind atoms. What makes them go from a gas to a liquid, or a liquid to a solid. So the first thing you should know is understanding, why do states of matter exist in the first place? Why doesn't everything just exist as a gas? And the idea is we have two different opposing forces. All atoms will always be in motion. As long as they have temperature, they are in motion. Now the amount of motion depends on their kinetic energy. Kinetic energy is the energy of motion, and it's essentially trying to pull all atoms apart. Now, if they have a lot of kinetic energy, they're running around like madmen, they're a gas. But atoms with little amounts of kinetic energy would be like wiggling in place, like a kid with ADHD asked to sit still during class. So they're a little squirming in place, but for the most part, they are not really moving. So the other opposing forces is what we call intermolecular attractive forces. So I specifically say inter as opposed to intra. Intramolecular forces are forces within a molecule, such as covalent bonds and ionic bonds. But intermolecular attractive forces are forces between different molecules that are going to bring them together. In general, intermolecular attractive forces are weaker than the ones within the molecule. But so the push-pull of these intermolecular attractive forces and kinetic energy is what separates our three states of matter: our solids, our liquids, our gases. The gases generally have very low intermolecular forces and a lot of kinetic energy. So they're moving fast and they're not really able to be captured and slowed down. Solids have very little kinetic energy and have lots of attractive forces. Of course, liquids have similar amounts of each. So they're able to slosh over each other, but they're not really able to they're able to kind of move, but they're not really able to escape and to get by themselves. So, as I said, intramolecular forces are like ionic, metallic, and covalent bonding that keeps the atoms into a molecule or some sort of framework, which we'll talk about later when we talk specifically about solids. But intramolecular forces control reactivity. You have to break bonds in order to react. So the stronger the intramolecular forces, the less reactive a molecule may be. But intermolecular forces control things like some of our physical properties, such as boiling points. How much does it take to go from a liquid to gas? Melting points. How much energy does it take to go from a solid to a liquid? Enthalpy of vaporization and enthalpy of fusion, which is the energy that takes it to convert states, not just what temperature it occurs at, as well as other macroscopic properties, such as density. All intermolecular forces can be collectively called the van der Waals forces that we talked about last semester. However, we will now break them down into different forces, which are largely ion dipole forces, are dipole forces, hydrogen bonding, and what we call London dispersion forces, which can be called instantaneous dipole, induced dipole. Sometimes it's just called van der Waals force, but we'll break them down bit by bit. But so, intermolecular forces. Largely, it's all about electrostatic attraction. Kind of the same idea of magnets, that a North Pole magnet creates a field that attracts a South Pole magnet, and the positive and negative try to come together. Same way ionic bonding. Well, dipoles work in the same way, that dipoles are just a weaker form of ionic bonding. So, in general, the stronger the charge, the stronger the attraction. A stronger magnet has a stronger pole. The largest charge possible, of course, is a straight-up ion, where we've completely lost an electron or completely gained an electron. So you can't get much stronger than that unless you make it two ions, like a 2+ charge or a 3+ charge. But for the most part, ions are generally the strongest attractive force. But the next strongest will come from dipoles. Our dipole, remember, we have to draw a Lewis structure, but it's the partial charge that comes with differences in electronegativity. So we're pulling the electrons from one way to another, from one side to another, and that creates a partial positive and a partial negative. The electrons are spending more time on the left than they're spending on the right, and so the left side is more often negative than the right side, and so it becomes a net negative and a net positive difference. And so anytime you have a polar molecule, they have a dipole. But the lowest type of intermolecular forces come from nonpolar atoms. Many of our organic molecules have these are made up of nonpolar atoms, and so they still have some attraction. But how does it work? How does it work? So, starting with the usually considered the highest, which is ion dipole. Ion dipoles is just an interaction between any sort of ion and a polar molecule. It is the simple way of why any salt dissolves in water. You need a strong interaction in order for this to go. And so you can't get much better than ion dipole unless it's ion-ion. Now the cation is attracted to the negative side of the dipole, and the anion is attracted to the positive side of the dipole. So this is the force that comes after an ionic solid dissolves in a polar solvent. Well, the question is, why do the ions break apart in the first place? The ion should be a stronger force, but largely speaking, water has the advantage of numbers. Simply put, that the crystal structure, they do not always pack the ions super tightly, and water molecules can slip between the crystal structure, and if it slips between the crystal structure, it can essentially grab, surround, and drag off ions. That for every one cation, you have 4 or 6 waters surrounding it. And so you have all these waters surrounding it. It helps separate the cations from the other anions. And then the anions can be separated and surrounded by 4 or 6 other waters. And so you slowly drag them off. But some structures, the ionic forces are too strong, as we'll see later on in the semester. And so they don't really dissolve in water. Even though they're ionic, we don't have a good interaction. And that's also why there's a limit on solubility. You need so many water molecules to dissolve these salts, so you need enough numbers of water to completely dissolve it. Well, if you don't have enough water, it's not going to fully dissolve. So we need enough water to break up the ionic forces, and then it's stabilized by the making of these ion dipole forces. Well, we're going to skip hydrogen bonding just so we can talk about dipole-dipole. Now, dipole-dipole is the interaction that comes when we have two different types of polar molecules. Once again, you have the positive end of one molecule being attracted to the negative end of another. Almost any liquid, if it's polar, will do this. I mean, this is why acetone and ethanol dissolve in water very well. Acetone is an organic molecule that has a carbon double bonded to an oxygen. Acetone is almost infinitely soluble in water. Ethanol, it's a 2-carbon hydrocarbon with an OH. The OH is the polar end. It dissolves in water 100%. There's no amount of ethanol that will not dissolve in water. But this is where we get some of our ideas that polar molecules will dissolve in any other polar molecule. The higher the polarity, the greater the attractive force, the more the solubility. But what makes a liquid is that these dipole bonds are not really stuck in place. The atoms are allowed to move. They're going to make bonds as they get close enough to see the attraction, but they're also going to break bonds as they're moving. And so they're going to constantly be making and breaking for these bonds as they're sloshing around into each other. Thus, you see the liquid water. Only once you hit a solid, when you cool them down enough that they can't move and can't break these bonds, that they start to maximize the number of bonds and arrange themselves in some sort of matrix, which face might be blocking up part of this, but you can see solid water in the form of ice forms these hexagonal shapes that are made by the need to maximize the number of bonds. And so this results in a little gap space between atoms that increases the volume that water takes up, thus decreasing the density. So ice floats because of this need to maximize the number of bonds. Well, now dipole is the next best, but really hydrogen bonding is better than dipole. But hydrogen bonding is a specific type of dipole interaction that only comes with certain special types of atoms. And this is extra strong due to there's a very large polarity difference between certain highly electronegative atoms and a hydrogen atom, thus the hydrogen bond. The idea that hydrogen is essentially a proton and a lone electron. Every other atom, regardless of how electronegative it is, has some amount of core electrons that even if the outer valence shell is completely removed, these electrons remain. So even in cases like lithium, where lithium plus 1, we've completely removed the valence shell, but it has still 2 core electrons that it's shielding the nucleus. Well, hydrogen only has that 1 electron shielding the nucleus of 1 proton. So any sort of dipole interaction that extracts that electron leaves essentially a naked proton behind. And so that's where we get this idea of hydrogen bonding being extra strong, because it's essentially a naked proton with its essentially hanging out bare to the world, so it gets an extra strong positive charge. So these bonds need two things present. They need a hydrogen that is bound to one of three atoms. That could be a fluorine, that could be a nitrogen, that could be an oxygen. So an HF bond, an HN bond, or an HO bond. Now here's the other thing. They need to see another atom in a different molecule that also contains an N, an F, or an O. If we have any of those atoms, we can have a hydrogen bond. So this could mean intermolecular attractive forces between two different molecules of the same type, but you could also have intermolecular attractive forces of two molecules of different types. So water will hydrogen bond, because it has an OH, with any of the other molecules shown. HF can hydrogen bond with any of the molecules shown. The F can hydrogen bond with the H on ammonia, NH3. And the lone pair of ammonia can hydrogen bond to the H on HF. On the far side, we have methanol, which is a CH3OH. That can hydrogen bond to other methanols. But it can also hydrogen bond to dimethyl ether. Dimethyl ether with its CH3OCH3 cannot hydrogen bond with itself, but it can hydrogen bond with methanol. So I'm going to draw a quick example real quick. So just looking at this, this is the structure of acetone. Carbon, O, lone pair, CH3, CH3. Okay. So this guy cannot hydrogen bond to other acetones. It has a dipole, but it cannot hydrogen bond to other acetones because there is no there's no OH bond. There's a CH bond, but no OH bond. So they can definitely have a dipole, but you cannot get a hydrogen bond. However, I put in a single water molecule, and suddenly we have hydrogen bonding. So we put in a water molecule, H, O, H, and suddenly we can hydrogen bond, and that's because we see that this interaction, the OH interacting with the O of this molecule. That's what I mean when I say this guy can hydrogen bond to this molecule, but it cannot hydrogen bond to itself. Water can hydrogen bond to itself, and it can hydrogen bond to any other molecule that contains an O, or O, an N, or an F. The last force is London dispersion forces. It's one of the trickier forces to understand. So if all these attractions are coming from polarity, a difference in electronegativity, the idea of a dipole creating a small charge that can be attracted to a charge on another molecule, why do non-molecules stick together? Why aren't all organic compounds gases? Well, a lot of them are. Methane is a gas. Ethane is a gas. Propane is a gas. But butane, we're starting to get into liquids. You go pentanes and hexanes, it's starting to get into liquids. You get heavier and heavier and heavier, you finally get into essentially solids. But so, why are some of these liquids and solids? And it has to do with London dispersion forces. The idea is that we have to go way back to our properties of light. The idea that when we're thinking of electrons slinging around the atom in their little like shells and their orbitals. These are constantly in motion. We don't have a set path that they can go. They're like, imagine the electrons are cars driving on a highway. We have little lanes where they're supposed to be at. Little lanes where they're supposed to be driving. But they can move around. They can swap lanes at will. They can move around within the lane. If the car next to them starts to drift into the lane, they can try to shift over a bit. And that's essentially what we have. Electrons are constantly orbiting the nucleus. Within an atom at any given time, at any given instant, we can have essentially electron asymmetry within the molecule. If you average out the whole molecule, all the electrons equal out in the long run. But at any given instant, you could have more electrons on one side versus another. When you have that, you create an asymmetry. This asymmetry creates what we call an instantaneous or momentary dipole. So the electrons are shifting to one side, and for that briefest of brief instants, you get a negative charge on one side and a positive charge on the other. Now, this instantaneous dipole can induce a similar asymmetry in adjacent atoms. Essentially, a car starts to drift into your lane. So in order to avoid him, you start to drift to the right, because he's drifting from the left to the right and into your lane, and you start drifting to the right, and that causes the next car to start to drift to the right, because we're all trying to avoid hitting the guy who's drifting into our lane. And so this is the instantaneous dipole that induces a dipole in the atom beside it. Now these are short-lived, because maybe like someone honks the horn, guy realizes, shoot, I'm drifting into someone else's lane, he gets back where he's supposed to go, and so the distortion is gone and everyone gets back how they're supposed to be. But the fact that these can form a lot, these can form infinite number of times, a whole lot, that is just, on average, you don't see a whole lot of them. It's not a very strong effect, but it can cause minute attractive forces on neighboring atoms and slow them down. Now there's three things that can increase the strength of this London dispersion forces. One of which is polarizability, the other guy is size, and the other guy is shape. Now, polarizability is probably the hardest to understand, but it's the idea that the more weakly the outer electrons are held, so essentially the better shielded they are, the farther they are from the nucleus, the more shielded they are, the easier it is to polarize them. So they're not really held real strongly and kept into the lanes. They're kind of swerving back and forth, moving very wildly, and so they can shift very easily. Generally speaking, this is also related to size. Bigger atoms with more valence electrons see greater polarizability. So iodine with its, let's see, how many electrons would that have? Like 53 electrons is far more polarizable than bromine with its 35 and chlorine with its 17. So even though the molecules essentially would look the same and act the same, chlorine is a gas because it has weaker London dispersion forces. Bromine is one of the few liquids we have because it has a little bit stronger, and iodine is one of the few well, it's not one of the few, but it's a solid version of this, and because it's extremely polarizable and can easily make a lot of London dispersion forces. Now there's also a strong relationship between the sheer number of electrons and the ease of polarizability. So the larger the atom, the easier it is to polarize, because we don't need to polarize every single atom at the same time. We just need to polarize one of the atoms along that line. So if you have 100 atoms, the likelihood of polarizing even one of those is very high. Maybe you're going to polarize several of those atoms, and so you get a lot of different attraction at any given time. So methane, with its 1 carbon and 4 hydrogens, not a whole lot of electrons, not very polarizable. Hexane, with its C6H14, it exists as a liquid. It has a lot of atoms that can easily polarize. But C31H64, you're getting into fats and whatnot. You're getting into things that can essentially exist as a solid. You get a lot of different attractive forces. It's going to keep it locked in place. So it's going to be 1,000 little hands grabbing the other atoms and pulling them in. Even if it's just a quick grab, it doesn't grab it for very long. It still grabs and pulls it in. And the last thing is the easiest one to see, and that's shape. Shape has a direct relationship to surface area. The larger the surface area, the more contact atoms can have. If you want an atom to polarize and you want it to essentially grab onto other molecules, the more places it can touch the other molecules, the more likelihood you're going to grab onto them. So long, flat shapes tend to have a large surface area, and thus can create a long London dispersion forces that will increase the attractive forces overlapping. So look at pentane, which is C5H12. Boiling point of 36, which is not very high, but still very moderate. Density, it's a little bit, 0.626. The 2,2-dimethyl propane, C5H12, same carbon count, but the boiling point drops to 10 as its density drops down by just a bit. It's a little bit bigger molecule, so it can't pack as tightly, and so you see the density going down, but you see the boiling point drops by 25, 26 degrees. This is a gas at room temperature. The other one is a liquid. That's because if you look at it, it's like a tripod. Unless you fold up the tripod, it's kind of hard to store it any place. That tripod takes up a lot of space, and so you can only really interact along any one of these one bonds at one time, as this one could interact over this entire surface. So like a blobby couch, you can stack them on top of each other. This one can only interact from here and, like, say, there. So the longer, the more surface area you have, the greater the interaction you can have. That's another reason why these long molecules are usually more polarizable. But so in general, to summarize our forces from weak to strong, we have our London dispersion forces, which are our instantaneous dipole and induced dipole. They occur within every molecule. Every molecule has some London dispersion forces. However, if you have it's like everybody has some loose change in their pocket somewhere, but some guys have some cash, some bills. If you have some bills and you have loose change, you're going to try to pay with the bills first. You're not going to try to dig around and count out pennies to pay for something. You're going to go with the big bills first. So this only really affects nonpolar molecules where they only have London dispersion forces, but everything has them. Dipole-dipole forces, which occur between polar molecules. Hydrogen bonding, which is a special type of dipole-dipole that has a condition of you need a HF, HO, or HN. But once you have that, they can bond with any other O, N, or F. Finally, ion dipole, which occurs between ionic molecules and polar molecules. So we'll end this video by giving a quick practice of identifying the intermolecular forces and predicting their boiling points. So, looking at this, we have water, we have hydrogen, we have sodium chloride, we have dimethyl ether, and we have methane. So, the first one, you can use properties you know about this. The first one, the highest one, would probably be sodium chloride, because sodium chloride is a metal mixed with a non-metal, which is going to have straight up ionic bonding. What is this at room temperature? This is a solid. Solid at room temperature is probably going to have, if it has a high melting point, it probably has a high boiling point. But ionic bonds are even stronger than ion dipole. The next highest force is water, which could hydrogen bond to itself. You already know the boiling point of water is 100 degrees. So that should be pretty straightforward. The next one is we have two hydrocarbons, and we have one hydrocarbon that includes an oxygen. Dimethyl ether includes an oxygen, so it is polar. However, it does not have an OH bond. Because it does not have an OH bond, it can only be dipole-dipole. So while it can be in liquid near room temperature, it has a very low boiling point. But you could easily turn that into a liquid. The last two, methane and H2, are both hydrocarbons that are gases. But in looking at this, neither of them have polar molecules, so they both have London dispersion forces. But in terms of sheer amounts of size, methane is bigger and so would have greater amounts of London dispersion forces than H2. And so H2 would see the lowest boiling point, methane being one of the second lowest. And so that's how we would arrange these based on that. With that in mind, this is Andrew signing off.